Okay, let's dive right into one of the absolute deepest mysteries in all of physics. How does our solid, predictable, everyday world actually emerge from the strange, hazy, probabilistic quantum realm? I mean, this is a question that has stumped the greatest minds for a solid century. But a powerful new idea, one that's inspired by Darwin himself, might just be the thing that finally brings our fuzzy reality into sharp focus.
So what do you think is the single biggest puzzle in modern physics? It's probably not what you'd guess. It's not about finding some new exotic particle or a new force of nature. No, the real head-scratcher is something we experience every single moment of our lives, but we can't really explain it. The very nature of reality itself.
You see, we've gotten incredibly good at figuring out the fundamental ingredients of our universe. The quarks, the leptons, the bosons, the whole shebang. But just knowing the ingredients in a recipe doesn't tell you how the meal gets cooked, right? The real puzzle isn't the what anymore, it's the how.
Right. The true mystery is that transition. How does that uncertain, shimmering world of quantum possibilities somehow collapse down into the one, single, solid reality that we all share and agree on?
This sculpture right here, Antony Gormley's quantum cloud, is pretty much the perfect metaphor for this entire mystery. When you get up close, it's just a chaotic mess of steel rods. But as you step back, a clear human form starts to emerge from the chaos. That's our problem in a nutshell. How does a definite, solid reality emerge from a probabilistic haze?
So, to really understand the solution, we first have to appreciate the problem. For about 100 years now, physics has been kind of split, living with two totally different descriptions of reality that just don't seem to get along. On one side, you've got the quantum realm. It's a fuzzy world of pure probability, where particles can be in many places at once, in a state we call superposition. And on the other side, you've got our world, the classical world, where a book is either on the table or it's not. There's no in-between. Physicists called this divide the cut, and for decades, nobody had a clue how to bridge it.
So what is this superposition thing? Well, it's really the core of all quantum strangeness. The best way to think about it is like a spinning coin. Before it lands, it's not heads and it's not tails. It's sort of both possibilities at once. That's a superposition. A quantum particle, before we measure it, exists in that same kind of state, with all its possibilities existing at the same time.
For years, physicists were like detectives on a tough case. They came up with all sorts of clever and, some might say, pretty fanciful explanations for how the simple act of looking at something makes all those possibilities snap into one.
Some of the early ideas talked about a mysterious, random collapse, where reality just snaps into place for no clear reason at all. Others just sort of gave up and accepted that artificial cut between the quantum and classical worlds without explaining it. And of course, there's the super famous many worlds idea, which says every possible outcome does happen, just each in its own separate universe. And while that's a wild idea, all these theories either create new mysteries or ask us to believe in things we can never, ever prove.
But what if the solution didn't require some brand new, unprovable element? What if the answer was right there all along, hidden inside the rules of quantum mechanics itself? Well, that's the path that physicist Wojciech Zurek took, and it led him to a really crucial clue: quantum entanglement.
And hey, even Erwin Schrödinger, the guy with the cat in the box, knew how important this was. He called it the characteristic trait of quantum mechanics. So what is it exactly? Basically, whenever particles interact, they can become entangled. And that just means their individual quantum states, all their possibilities, merge into one single shared state. Their fates are now tied together. And here's the absolute key. This is not some rare exotic thing. It's happening constantly, everywhere, all the time. Entanglement is the main way information gets passed between the quantum world and our world. So, this constant universal entanglement, that's the first part of Zurek's big breakthrough. It explains why we don't see all that quantum weirdness in our day-to-day lives. It's not that it isn't there, it's just that it performs this incredible vanishing act.
Think about it like this. Imagine a single drop of dark ink. That drop is a particle's quantum superposition. Now, what happens when you drop it into the ocean? The ink instantly starts to spread out, getting diluted into the vastness of the water around it. The information, that drop of ink, is still technically there, but it spreads so thin across trillions of water molecules that you could never hope to put it back together.
This process is called decoherence, and the speed at which it happens is almost impossible to imagine. For just a single grain of dust floating in the air,
its superposition of different possible locations is wiped out in about a femtosecond. That's a millionth of a billionth of a second. In an instant, all that delicate quantum stuff is just washed away by the environment, making it completely invisible to us.
Okay, but decoherence only explains why we don't see the quantum weirdness. It doesn't explain why we do see a single, stable, classical reality. And that brings us to the second, and honestly, the most brilliant part of this theory, a kind of natural selection for reality itself.
So here's the whole path from quantum to classical. It all starts with a system in a superposition of all possible states. Then it interacts with its environment and gets entangled. That leads to decoherence, which dilutes all the fragile quantum properties. But, and this is the absolutely crucial step, some states are tougher than others. Zurek calls these pointer states. Think of things like an object's position. They're special because they can actually survive that interaction and create millions of identical copies or imprints of themselves all over the environment.
And we are not talking about just a few copies. The amount of information being copied is just staggering. Get this, in a single microsecond, that's 1/1,000,000th of a second, photons from the sun will create about 10 million stable imprints of a single dust grain's location. 10 million.
And that is the very heart of quantum Darwinism. Only the fittest states, the ones that are stable enough to get copied millions and millions of times, survive to become part of our shared classical world. This is why reality is objective. The environment gets totally flooded with countless identical imprints of an object's properties. So when you and I look at that dust grain, we both see it in the exact same place. We agree on its reality because that's the only information that survived.
So you can see, this theory is a massive leap forward. It actually promises to reframe a debate that's been going on for a century by elegantly combining the best parts of the older ideas.
See, the old debate basically boiled down to this. Is the quantum wave function, the math, just a description of what we can know about the world? That's the epistemic view. Or is the wave function describing what's truly, fundamentally real? That's the ontic view, which kind of leads you to the many worlds idea. For decades, you basically had to choose. Was it about knowledge, or was it about reality?
Zurek's genius was to say, hey, why choose? It's both. He calls his view epistemic. The quantum possibilities are physically real. That's the ontic part. All those different paths for a particle actually exist. But then quantum Darwinism acts like a selection process, picking only one of those paths to be copied over and over, making it the one we can actually know, and that's the epistemic part. It's just this beautiful synthesis of two views that were seen as opposites for so long.
Now, of course, the case isn't completely closed. Quantum Darwinism provides an incredible framework, but there are still some really big questions, like what is the exact mechanism that selects one specific outcome over all the others, and at what point does that choice become totally final and irreversible? These are the kinds of fascinating puzzles that are going to drive the next generation of physicists.
Still, even with those open questions, quantum Darwinism offers a profound new way to see the world. It suggests that the solid, objective reality that we all just take for granted isn't some fundamental feature of the universe. Instead, it's an emergent property. It's the winner of a relentless cosmic competition. The world we see is the world that was stable enough to survive being observed. Which leaves us with a final, pretty wild question to chew on. Is reality itself just a matter of survival?